this is our simplest supported beam. We have 3-point load in top of it, 5 kips, 10 kips, 15 kips. And I gave you the reactions, so I'm pretty confident that you guys all know how to calculate your reaction. If you still have difficulty in doing so, please make sure you see me and we can go through those, right? And with that, right, first thing that I will do is I'm going to drop the line from the starting point, end point, too much, and then I also going to drop the line at the locations of the point loads because I know that my shear diagram going to change at that particular point. To draw your shear diagram, you should know it by heart now. It's very easy. So you start from 0. Oh, let me change the color to, how about blue? So you start from 0 and you meet this 12.5 support load going upward. Therefore, your shear diagram is going to go upward, right? And that is shear diagram in kips. That is 12.5. And there's no point load in between. Therefore, your shear diagram is going to be constant. Therefore, it's going to be a straight line between those 2 points. And then you meet this 5 kip going downward. Make your shear diagram jump back down for 5 kips. You started from 12.5. You jump down for 5. That gives you 7.5. Good. 7.5. And then you just no point load in between. You go straight again. When you meet this 10 kips, you're going to drop down for 10. You start from 7.5. You drop down 10. That would give you 2.5 negative, right? You go straight again because there's no point load in between, and you meet this 15 kips. Then you drop 15 kips, becomes a negative 17.5. You go straight again. Before you meet this 17.5 load, that will bring your shear diagram back to 0. Right? That is basically your shear diagram. You start from 0, you end at 0. That gives you confidence that your reaction force is actually correct, right? All right, with the shear diagram now, of course, you can cut the beam and expose the external force to find out the moments at each point, and then you draw your moment diagram that way. But that is very time-consuming and tedious. And with the rule of thumb, the relationship between your shear diagram and moment diagram, we should be able to get your moment diagram directly without doing all those by summing the area of your shear diagram. Because the rule of thumb is the area of your shear diagram from left to right, if you sum those up, is going to be equal to the number of your moment diagram at that particular point, right? All right, to do that, let's make some note. Let's say this is, I'm going to use green. This is my area 1. This rectangular block is my area 1 here. The second one is my area 2. The third one is my area 3. And the last one is my area 4. I first calculate the area because later on I'm going to sum the area to find my moments. My area A1 is equal to, the height is 12.5 kips times the width is 3 feet. That would give you your 37.5 kip feet. Area A2, that is 7.5 kips times 3 feet. That would give you 22.5 kip feet. Same for A3 and A4. A3 is negative 2.5 kips times 3. That would give you negative 7.5 kip feet. A4, negative 17.5 kips times 3. That will give you negative 52.5 kip feet, right? And now we can find our moment diagrams. I'm going to use blue again. Your moment diagram always also start from 0 because we don't have any concentrated moment at the end, right? Because of equilibrium, therefore your moment is going to be 0 at the end. That's moment kip feet. And the moment at 3 feet, meaning the moment at this point that is equal to the summation of the area of your shear diagram, meaning that is your area A1, right? Your area A1, we calculate that as 37.5. Therefore, your moment at this point is equal to 37.5, right? Let's put that in. That is your 37.5, and that is equal to A1 is equal to 37.5 cubic feet. At the moment at 6 feet, the moment at this point is equal to the area of the shear diagram before that. So meaning that is your area A1 plus the area A2. That's equal to area A1 plus area A2. That is 37.5 plus 22.5. That would give you 60 cubic feet. All right, let's put that back in. Here is 60. That is the second point of our moment diagram. Same thing, moment at 9 feet. That is area A1 plus area A2 plus area A3. Now all this area before that particular point, right? And that would give us 60 cubic feet. That is our A1 plus A2 plus A3. A3 now is a negative value, meaning that we need to subtract that out from the results. That would give you 52.5 cubic feet. Right now, the third point we have is 52.5 cubic feet. Right? To double. Now, what is the value moment for the last point? It has to be 0. And one thing that we can check is we can sum all the area for your shear and see if actually give you the 0. If not, then you're in trouble, right? Let's take a look. A moment at 12 feet, that is going to be A1 plus A2 plus A3 plus A4. That would give you 52.5 cubic feet. Minus A4 is 52.5 cubic feet. That gives you 0. Okay, good. So we confirmed it. Now we have all the dots in our moment diagram. How to connect them? We have straight line, we have parabolic shape, we have curve shape. What do you think? Straight line, good. Why straight line? There's actually one of the rules of thumb that we found can confirm that's a straight line.
Value of the
slope
shear.
of the
Oh, slope, I hear slope. Okay, good.
slope of the moment diagram is the value of the, or is the,
What was that? What was that?
force of the shear force?
Shear force? Anyone else?
Value of the shear force is the slope of the moment diagram.
Okay, good. So the value of your shear force, the value of your shear diagram, right, is actually shear force is actually the slope of your moment diagram. Okay, let's take a look at this portion of your shear diagram. It's a constant, right? For constant slope, what kind of curve will give you a constant slope? It's a straight line, right? So meaning in this particular line between these 2 points has to be a straight line because your shear diagram is a constant between those 2 points. Yeah? Yes?
So for example, if you have like a moment, like in the homework, you would like just subtract it or add it in that one.
Right. So it seems like everyone is stick to the homework. Huh? Yes, if for example, if you have a concentrated moment at this point, for example, then you're going to have this 60 either drop or jump before you add the other area in there. Make sense? All right. So with that, now we know that those connecting those dots has to be a straight line. Let's do that. Let's connect those dots with a straight line, straight line, straight line, and straight line. Right, and this is our moment diagram. Right, and with that said, if we need to know any point between those two, what is the moment for those? We can just simply do the interpolation, right? we know those 2 points. If you would like to know any moment between those 2 points, you can just find it through maps. Okay? Any questions? Great. No question, I have a question for you. That's always the case, right? And for this particular case, where do you think is the most likely point that the beam is going to fail under shear?
The 15 kip highest, 15 kip more?
This point here?
Yeah. It has the most shear.
Good. What else? Any other opinions on this? Everyone agree that is this point here?
Also has the highest.
This is 17.5 negative, right? It's good. It's a very good observation because we have the maximum shear at this point. However, the whole section actually just has the same shear, right? So if it's going to fail, most likely this area is going to fail because it all has the same shear. Yeah. What about the moment? If your beam is going to fail under flexural loads, meaning moments, which point or which section do you think is going to fail? This guy, right, has a maximum moment, right? Yeah. Okay. So just to highlight those. I'm gonna use red. So this portion here is the portion most likely to fail under shear, and here is the point most likely to fail under flexural. By the way, we typically call factual for moments, and you can always go moments. All right, good. Let me save this.